Our next speaker, Scott Inman, has been working in the product development industry for the past 38 years, 20 of which with the Mycorrhizal Applications Company, developing fungal and bacteria agricultural products. In his current role as Director of R&D, he leads a technology development team that works on projects in over 30 countries in more than 30 crops. A large focus of his research is focused on mycorrhizal fungi and their role in health and plant productivity. And that is what he's going to speak to us today about in his lecture entitled Mycorrhizae 101.
All right. Thank you very much, Robert, and welcome everybody to this webinar. Today, I'm going to talk to you about mycorrhizae, which I had a great introduction from the previous presentation. So first, the question is talking about mycorrhizae. Is it present in the soil? There's a lot of organisms in the soil. The key thing about mycorrhizae, once it leaves the system, it's very slow to come back. So there's a lot of discussion about, is there mycorrhizae in soils? The key here is that, you know, you're going to have to inoculate once it leaves the system. There are, you know, histories of cultural practices in our agriculture that have been very detrimental to mycorrhizae, as well as soil fungi, and some of those are fallow periods because of the association of mycorrhizae has to have a plant to function. Tillage is very detrimental to the hyphae, and then non-mycorrhizal plants. So you have this longer fallow period if you're planting non-mycorrhizal plants. Hey, Robert, which screen are you guys seeing? The right one, the full screen?
Yes, it looks good.
Okay, thank you. So there are 7 types of mycorrhizae that are important. So these are kind of associated with all the plants. So arbuscular mycorrhizae and ectomycorrhizae, they're the dominant ones, and they're the most, for agriculture, they're most, but we do have 5 others that do. You have orchid, you have iricoid for like blueberries and ornamentals. But the dominant, like I said, is arbuscular mycorrhizae. So this is based on the plants around the world. So it is associated with about 80% of the world's plants, the arbuscular mycorrhizae, and then the ectomycorrhizae associates with about 10%. So these 2 types of mycorrhizae associate with 90% of the world's plants and most of the agricultural plants, except for something like blueberries. And then your other 5 types with about 5%. And there are about 5% of the world's plants that do not form. So somewhere along the line, they lost their ability to form an association. And those are like your brassicas, your mustards, spinach, and a few other. A lot of the weeds do not form with mycorrhizae. But so that's kind of the makeup of the way the association forms. So let's talk about the mycorrhizae and the functionality and why, as it was described in the previous presentation about root and functionality. So we'll start with ectomycorrhizae. Both types of mycorrhizae penetrate the root. The difference is ectomycorrhizae just go between the cells. And this is mainly for your trees, your hardwoods, evergreens, and in the ag world, you're talking like pecans, hazelnuts. Those are ectomycorrhizae type crops. And we're going to spend most of the time, because most of the crops are arbuscular mycorrhizae, they form an association. So we'll spend most of the time talking about the functionality and the benefits of arbuscular mycorrhizae. So a key thing about the association is that the plant is the driver. It is one that's turning on and off the relationship. If the plant doesn't have a benefit, it can actually turn off the functionality. So, and it can actually form with many mycorrhizae at the same time, or turn those on and off as the needs through the season. And kind of how this works is the plant would send out a signal that it wants to form association, and this is usually triggered by some type of stress, either nutrient or water or other stress, and then it would that signal would cause the spore to germinate. The hyphae would germinate, it would penetrate the root, and then it would actually penetrate the cell. And then these structures, arbuscules, would form. And so these is where the exchange happens between the plant. And in association, the mycorrhizae can actually get everything it needs out of the soil except for one component, and that is carbon. And that is what the plant is providing to the mycorrhizae in exchange for it to bring nutrients and water back to the plant. So everything is happening at this cell level at the arbuscule. So the trigger is the plant was working with the mycorrhizae, providing a carbon, and in exchange, the mycorrhizae is wanting the plant to develop. So it's going out into the soil and acquisitioning nutrients and water. And so a couple of the key structures, like the arbuscule, this is where the exchange happen. Vesicles are structures that is the hyphae that swells, and these become storage units. So in times of excess, the hyphae can swell, that'll store waters and nutrients in the form of lipids, and then it can use it later. Hyphae is the structures that go out into the soil. This is where you collect the nutrients and water. It takes it up into the hyphal network, and then it transports it back. So that's one of the unique things about mycorrhizae. So once it's taken up into the hyphal network, it's accessible to the plant, and it's in that hyphal network. Spores are the dormant structures. And then propagules are important because that's what you see in products. That's been defined in the regulatory and AFCO. They've defined active ingredients as propagules, which are combinations of spores or colonized root fragments. So I'll give you some visuals here. If you see on the left, the blue, you can see the round structures. Those are vesicles. Those are the swelling of the hyphae. In the middle, you can kind of see the arbuscules. Those look like little trees. And then the lines are the hyphae. On the right, you can see a non-colonized root. Here's a little more magnified at the cell level. So you can see the arbuscule where the exchange happens. It's in the cell. The tubes that you see that are magnified, those are the hyphae. So they're coming directly to the arbuscule where they exchange for carbon, and then it's bringing nutrients and water to the plant. And then you can kind of see the hyphae, and the reason the hyphae can go out into the soil, it's very small. It's about 1/10 the diameter of your hair, but you can see some free spores, and then how small the hyphae is in comparison to a root and a root hair, as described before. And then this is what it looks like. There's as far as propagation, there's some free spores, and then also certain species and interactions with the plant, they will actually form spores within the root fragment for future generations of the mycorrhizae. So let's talk about soil health. Mycorrhizae is a little unique in a comparison to a lot of the other organisms because of its association with the plant. So it's got a more of a short and a long term, and a short is season long or the life of the plant. So in general, mycorrhizae stays with the plant for the duration of the plant cycle. So if you got an annual versus a perennial, or the mycorrhizae is with that plant, and it's driven by that relationship. So there's some in-season benefits. We'll go into those in more detail as we go along here, but the big ones are increasing the access in the soil, water acquisition, and nutrient acquisition. So the hyphae are driving that. They can bring it back. They make the plant more efficient because the plant is only investing carbon, and the mycorrhizae is doing all the other work. And as we're talking about today for the soil health, this is a longer term. So specifically, arbuscular mycorrhizae produce a glycoprotein glomalin. So it's called soil glue. We'll talk a little more detail about that, but it is really key in soil health because it's all about the soil structure. To actually acquire soil structure and the soil health, mycorrhizae is very important in that component because you need the soil structure. Once you get that structure, you increase your water holding capacity. And then because of the microbial biomass and the glomalin, the carbon, and microbial diversity, as well as the microbial biomass, is all linked to our Muscular Mycorrhizae, which we will continue to discuss that as we go along. So it's really a significant component. So if you're talking about soil health, it is very important that mycorrhizae is part of that equation. So here's some of the benefits. Mycorrhizae have been around a long time. It's recognized as one of the most dominant organisms in the literature. There's over 100,000 literature references to mycorrhizae and what it does and the different types. But these are just some of the key benefits that you can kind of recognize, and probably the most documented is nutrient uptake. The advantage that mycorrhizae has, and it's been documented, phosphorus, nitrogen, potassium, sulfur, a lot of the micronutrients. The unique thing is mycorrhizae can take up nutrients both in the available as well as the unavailable. And then once it does that, it transports it back through the hyphal network. So it does something like phosphorus that ties up really fast if it's not taken up once it becomes available, but it can transport it back to the plant. And again, it's very efficient for the plant because it doesn't have to expend much energy because it just has to give some carbon. Another unique thing about mycorrhizae, and especially in the desert Southwest, is the toxic soils and specifically salinity. Mycorrhizae has the ability to penetrate these soils, take up nutrients and water. They will filter out in this case, sodium, and then it'll transport the nutrients and water safely back to the plant. It actually keeps the sodium in the hyphae and keeps the plant safe. So that plant can actually be productive under these conditions. And then we'll talk about the advantage, because you know that sodium also breaks down the soil structure. So this glomalin will actually help rebuild the soil structure because it's really important about pushing the salts into past the root zone, and that's all about structure. The greater drought tolerance, as you can imagine, the hyphae can actually go into pore spaces that the plant can't, and especially under drought stress. It's only investing carbon, so the mycorrhizae is getting everything else, so it can actually more efficiently acquisition that moisture. But it also actually can collect it, put it into the hyphal network, and I talked about the vesicles. It actually stores it. So under these drought conditions, the mycorrhizae does a lot of the work, puts a lot less stress on the plant, and allows the plant to be a lot more effective. And then a key component today for the soil health is this glomalin production. It's very unique to our Muscular Mycorrhizae. It's very key on soil structure, and then it's very positive on the soil health. So these are the key. There's 25 or 30 well-documented benefits that mycorrhizae brings. But these are the key ones that if you're looking at agricultural production, these are kind of the benefits that we get from mycorrhizae, specifically our Muscular Mycorrhizae. So what, as we were talking about in the prior presentation, if you talk about a plant that does not form an association and it's working on its own, so you have the uptake is going to be at the root hair as it was described before, and it's only millimeters distance away, and that absorption only happens at the tip. And so then also the plant can only take up the available form. So it needs some kind of a microbial activity to free up that nutrient into available form so it can actually be taken up as it was described before. But if you look at once a plant forms an association with the mycorrhizae, the hyphae can actually grow out about 25 inches away from the plant, so it has a greater reach. Also, the uptake can actually be in the available and unavailable form. So that means that something like phosphorus, and that's why it's well documented, actually take it up as well as other nutrients. And the key here is that because it can take it up all along the hyphae, so wherever the contact happens, and then in the available, it's very efficient and not only for the plant, but also utilization in the soil. It allows the less runoff, less offsite movement because it's taken up into the hyphal network. And then this talking about the way nutrients get in, because it takes it up in the hyphae and transports it back. It's very efficient for the plant, and it will transport it all the way back into the root to the arbuscule in exchange for carbon. So what does that mean for a plant? So if you look at this, where a plant actually has access, where you look at the root without a mycorrhizae, you kind of call this a depletion zone. And even within that zone, the plant doesn't have 100% access. It has to be available, has to be in reach with the root hair and in the available form. But once you form the association, you got this greater extension out beyond the root zone that the mycorrhizae can actually reach beyond what the literature reference that you can actually increase your absorption area, and that's what the plant has access to by 50 times in this association with the mycorrhizae. So if you're looking at water efficiency, nutrient efficiency, this combination with the mycorrhizae and this association makes the utilization and the plant more efficient. And it actually has access to this for a lot more efficient than the energy it would have to do on its own. So let's talk about moisture stress, because that's, the desert Southwest. The structure development is very key on the soil holding capacity, or what it can hold, the spore space, and keeping it on. So that's all associated with the mycorrhizae, and I'll talk about aggregate development here in a minute and explain that a little more. But it's all about the not only the microbial biomass and the hyphae and the glomalin, but it's putting that soil structure together. So that's very key on. And then it's also developing the reserves. So this is some of this water holding capacity, but also the hyphae itself. It can actually hold quite a bit. It can develop the vesicles, so it can actually hold the reserves. Plant availability, it can actually, the root absorption, as I explained in the prior slide, it can actually get out in the soil. It can actually penetrate even under low moisture conditions. It can penetrate pore spaces that, that the root couldn't, especially under stress. And then, under stress, the plant actually function a lot better because it's only investing carbon, and in return, the mycorrhizae is doing all the work. So it's just exchanging that carbon for the nutrients and water, and allows the plant to continue on with minimal expenditure, but still function under that stress. And as I described, a unique thing about mycorrhizae, and especially in the Southwest and other areas where salinity is a real problem, and it's continuing to grow around the world. Mycorrhizae has the ability to grow into those conditions out away from the plant. It will actually can absorb the toxic elements with the nutrients and water alone, or as it's tied up, if it's carried in the water, and it will filter those out, keep it in the hyphae, and then transport it back to the plant all the way to the arbuscule. So it can allow the plant to be more productive even under these stressful conditions. And then in addition, specific to salinity, is this structure rebuilding with the glomalin, with the aggregate development. And so that allows for future reclamation of the soil, so you can actually get to a point to get enough structure that you can actually flush those salts below the root zone, which is very important on a long-term basis. So here's a little, kind of some visuals. If you look up in the top left, that's some grasses that are established, a very high saline on the beach. Those can only establish because of the mycorrhizae allow them to function. They can actually, the mycorrhizae can go into the soil, or the sand in this case, and acquisition nutrients and water, which would otherwise be toxic to the plant. Because you can see below that, here in fields, you got saline sodic situations where there aren't mycorrhizae, and the plants aren't able to survive. And on the right, you can see this is a mycorrhizae was treated on the left. This is cotton. You can see it's standing very tall. On the right is a non-treated under these drought conditions. The cotton is very wilted, so you can see a big difference. But the key here is the plant has acquisition to a lot more moisture than it does on the right. Plus, it's not expending the same amount of energy to acquisition that. So it's a lot more efficient and effective in its stress management. So we are talking about soil health, and some of the soil health indicators are your physical, chemical, and biological. And a lot of people talk about the physical and chemical, and it's just really recently people started adding in the biological, which is great. Key component of that is mycorrhizae. So you really can't talk about soil health without having mycorrhizae, and kind of describe why, because it impacts or affects all three of these pillars. If you look at aggregate stability, water infiltration, retention is all about soil structure. That's about the glomalin and the hyphae and its ability to put aggregates together. And I'll describe that in the next slide. And then the chemical, with carbon content, this goes back to the microbial biomass, as well as the glomalin, nutrient availability, the salinity management, toxicity, that's all associated. The arbuscular mycorrhizae is very important. And then the biological, it's a very difficult part of this pillars, but it's very important. And I'll describe about the organic matter and the importance of microbial biomass. But it's kind of like the mycorrhizae is a big biomass producer, and so the other organisms kind of rely on it to actually persist, and especially free living fungi, and we'll describe that a little later. So if you're talking soil health, you got to put mycorrhizae into the equation as part of that development. So it's very important, or it'll be very difficult to achieve your goals without it as part of your equation. So here's a little key thing from the USDA about building a soil aggregate, and kind of the formation is a slow process of the mycorrhizae producing the glomalin. It's called soil glue. It was first developed in the USDA out of Champaign-Urbana in the mid-90s. So it's not that old, and it's not been around or identified. It's a very difficult molecule to work with, but it kind of works that it starts sticking particles together, and then in combination with other organisms and the hyphae and the plant roots, you start getting this aggregation, and there's some physical processes that tighten this together, and then you get a very stable component. And the glomalin itself is pretty stable. I think it's could be just under 50 years that it could be pretty stable. So that's why once you get it into the soil and you get the structure, it's a pretty stable process. So here's a kind of a simplicity. This is some stuff from the USDA, what it looks like. But think about, if you're familiar with the treats, the Rice Krispie treats, it's kind of, we use the comparison that the marshmallows are the glomalin and the Rice Krispies are your soil particles. And that's kind of how this works. You put the two together and they start to stick together, and then you have a structure. And then, so that's kind of how the process works. So again, it's not been around that long, and there's a lot of work being going on now. There's a lot of researchers that are looking at this. It's a pretty evasive process, and trying to get pretty involved. So it's really a key for the future, talking about soil health. So I'm going to end up my presentation talking about the organic matter that's been already talked about, but I'm going to focus on this bottom bar, talking about soil microbial biomass, because this is really a key component in a healthy soil. This is what a healthy soil should look like. About half of the soil microbial biomass, which is a small part of the total organic matter, which is a small part of the whole soil. But it's really important that to maintain and actually optimize the organic matter is having this balance. And the key here is having about 50% of that soil microbial biomass as fungi. And this is a combination of free living fungi as well as mycorrhizae. Even though mycorrhizae contributes a lot to the microbial biomass, it's not the only fungi, and we need the other fungi because there's a lot of good degraders. They just can't maintain themselves without that type of biomass created in the habitat from the mycorrhizal fungi. So this is what a healthy soil look like. Unfortunately, this is what most of our soils look like. If you look at a less healthy soil, this bottom bar, you have dominance is the bacteria and the actinomycetes that is approaching 60 or greater % of the biomass. And if you think about that, the fungi are a lot bigger, they produce a lot more biomass, and to have bacteria as your largest part of your biomass. And the other key here is bacteria are great degraders. As you know, that if we didn't have bacteria, we'd be over our heads in waste, and they're heavy degraders. But we need the fungi to balance that, to keep that offset, and we need to keep regenerating the microbial biomass, and fungi is a big part of that. And without the mycorrhizae fungi in there, this is what we get this reduction, and the fungi just can't maintain itself. So if you're trying to work on your soils, you got to get your fungi up, and that includes all types of fungi, but it's really important, and finding that right balance. So that's it for me. That's about mycorrhizae and the importance on soil health. And I really appreciate everybody's attention and participation. And thanks again, Robert.